We want to look at creating a low-pass filter using our two main op-amp configurations. Here's our inverting case, here's our non-inverting case. So in order to do a low pass, that means at the high frequencies, our capacitor goes to a short. So we want to block the high frequencies. So we typically put our capacitor in parallel, or that means we're going to put our capacitor to ground. So that would be putting our capacitor right here. So let's see how we're going to do this. So our corner frequency is 1 over 2 pi Thevenin resistance seen by the capacitor times our capacitor. So we're going to come in here and we are going to find the Thevenin resistance seen between those two terminals. So when we do this, let's kind of redraw our circuit to practice doing Thevenin equivalence. So here is our RS. Here is our voltage source. And here is our R1. The op amp has a virtual ground. So this looks like that. This is R1. This is RS. So if I come in here and I'm going to turn off my independent sources, and then I see that my Thevenin resistance is equal to these two in parallel. So RS in parallel with R1. So in order for this to be a good design, we typically want R1 to be much, much greater than RS so that there's no loading, which now means that our R Thevenin is equal to our RS. Now, this is not a good design because you don't want your Thevenin equivalent. Sorry, you don't want your corner frequency to be dependent on the RS because the RS can change. So this is not a good design. So we're going to come in here and maybe we want to put our capacitor right there instead so that we have all of that. So now we're going to redo this. And so now let's redraw this. So this is our RS. This is our R1. This is going to be our Thevenin equivalent points, and then we have the virtual short of our op amp, and so now we see that our Thevenin is equal to 0. Well, that is also not good. The last place that we have is we can put our capacitor over here, and now our Thevenin is going to be equal to the Thevenin resistance looking into the op amp, which is equal to 0, and so this also doesn't work. So we can't put it at any of these points, so what we're going to have to do So we have to come in here and put our capacitor in parallel with our feedback resistor. Now we can't, doing the Thevenin equivalent up here is a little bit difficult. And so what we want to do is we want to go back to the definition of our equation for gain and rederive what the corner frequency is. So here, the equation for our gain is equal to minus RF over R1, which in this case is equal to minus ZF over R1 because we've added in a capacitor which has an impedance of 1 over j omega c. So we need to calculate what ZF is. So ZF is going to be equal to RF in parallel with 1 over j omega c, which is equal to RF times 1 over j omega c over RF plus 1 over j omega c. Multiply the top and bottom by 1 over j omega c, and we see that we get ZF is equal to RF over 1 plus j omega RFC. So now we're going to plug this ZF into our gain, and we get A is equal to minus RF over 1 plus j omega RF times C. all divided by R1. So now we're going to multiply the top and bottom by the 1 plus j omega RFC, and we get minus RF R1, 1 plus j omega RFC is our gain. And so we want to put this in the form so it's easier to see where the corner frequency is. And so then this is equal to minus RF over R1 times 1 over 1 plus JF over 1 over 2 pi RFC, which is equal to minus RF over R1 times 1 plus JF over F1, where the corner frequency F1 is 1 over 2 pi RF times C. So what we see here is that we get the same equation except for the Thevenin equivalent resistance seen by our capacitor is actually just the feedback resistor. But then we can just easily say if I want to get the corner frequency, I pick RF and RC to give us this equation, 1 over 2 pi RFC. Okay, so let's come over here to our non-inverting case and do the same thing. We don't need that resistor there. Okay, so again, how do we do it? If I come in here and put my capacitor here, it's not going to work. If I put my capacitor here, it's not going to work. We're going to do the same thing that we did on the other case, and we're going to put our capacitor right here, just like we did before. So now we're going to go to our gain equation. So now our gain equation is equal to 1 plus RF over R1, which is really equal to 1 plus ZF over R1, which is basically the same thing that we had here, except for now we get a 1 plus. So we're going to come over here and we're going to go A is equal to 1 plus RF over R1 times 1 over 1 plus JF over F1 where F1 is equal to 1 over 2 pi RFC. So as long as our gain is our mid-band gain is much greater than 1, we get the same thing that we did before, and so we're going to set our corner equal to the RF and times the C, just like we did before.